Okay, I think that should do it. Um, yes, as I was saying before, thanks everybody for joining us this morning. So we finished the summer school yesterday, and today we have a workshop. So this has been like a tradition during the years. In the summer school, we have the 3 days of the summer school, and then at the end we have a workshop. As I was saying, the first day the workshop is sort of trying to get a sort of more um, sort of a state of the art or researchers on very specific to get together to talk about very specific research problems that deal or that involve somehow GPs. So just to give you an example, 2 years ago we had the physics inspired Gaussian processes workshop. Last year we had causality meets probabilistic models. This year we decided to change it a bit to have something a bit more sort of software related. And this is an idea like people here in the group at JV had suggested some time ago to have a workshop on all these different software out there that allows you to do Gaussian processes in some form. Um, so I think the motivation that we have for this workshop is that we know that many of you perhaps don't come from a software engineering background or have necessarily a computer science background, and are always curious about perhaps how all these libraries were built and how they become such a big sort of product in a sense. And in during those processes, obviously there is a lot of good research software engineering practices, and we have encouraged the speakers to talk a bit about those processes and how these things are built from a team of people, and just usually not just a single person, but huge teams of software engineers and scientists helping to create these frameworks. So we have 5 different talks today. So the first talk is going to be by Zhen Wei. He has already been in the summer school talking about scalability of Gaussian processes and also a roundtable. And then we're going to have Aki Bettari from Aalto University. So Zhen Wen is going to be talking about GPy, which is, I think, perhaps the first Gaussian processes package in Python that I know of. And then I think Aki is going to be talking about Stan. And then we're going to have a series of short talks from Second Mind, talking about the different packages that they have available to do all sorts of models that we have been looking at the summer school, including deep GPs, GP regression, and I believe also Bayesian optimization. And then in the afternoon, we have people joining from the States. So we have speakers from Google Brain, Dustin Tran, sorry, and Zachary Nato, who are going to be talking about a bit of uncertainty in deep learning. And then at the end, we have Max from Facebook, who's going to be talking about BioTorch. And then the idea is to have like half an hour of short discussion that is going to be led by Javier. So I have to say that this workshop was mostly organized by Javier Gonzalez, who gave the talk on Bayesian optimization yesterday, and also was with us in the roundtable. So thanks, Javier, for organizing the workshop. And I think that's it. I don't know if Javier, do you want to add something else, or shall we just start?
Yeah, no, thanks to you, Mauricio. I think that's a great introduction. Yeah, I think I don't have anything to add, so I think we can go ahead.
Okay, so Zhen Wen, thanks. So I'll just introduce you again. So Zhen Wen Dai is a research scientist at Spotify, and he is well known in our community for having a very strong research software engineering skills. So very happy to have you. Very happy to have you with us talking about this. And I think you were perhaps one of the most active contributors to the origins of GPy. Yes, so please tell us about GPy.
Thanks,
Thank you.
Mauricio. First, disclaimer: I don't think I'm the biggest contributor. I did some contribute to some part of the GPy, but I will tell a little bit more details. But there are people that actually does way more than me. I don't want to take all the credit. And let me get started with the first talk of the today. It's my honor to talk about the GPy. So first, what is GPy? For people are not so familiar, GPy is a Python library available on GitHub about doing Gaussian process modeling, inferences, and also some experiment as well have been used both by machine learning researchers, but also by some like people who like to use GPy to do some analysis. Typically, I know, for example, people from biology domains also apply this to like, for example, data analysis, especially low data regimes, it has been quite handy. Let's start it with the starting point of GPy. So GPy has been a product from Neil Lawrence Research Group at the time from the Sheffield Universities, and we are located in the office in the building or in a building called the Citron Sheffield Institute for Translational Neuroscience, because at that time Neil held a joint professorship between computer science and neuroscience department. And on the left side are the main contributors of GPy. Neil, before GPy, he actually had a MATLAB library for Gaussian protocol, GPMAT, and then that brought the team into the idea of having a Gaussian processor, a better Gaussian processor library, because I remember that time the GPMAT was developed with object orientation in MATLAB when the time object oriented does not yet exist in MATLAB. Long history, and then I think I joined a bit later after the GPy project already started. But from my memory, I think James and Nicola, James Hansman and Nicola Fusi started the ideas about having the software library, and then there are a few main contributors. For example, Max did a lot of the infrastructural work and some of the GPLVM models in GPy. Alan did quite a lot of the non-Gaussian likelihood component, and Mike Croucher, I think, joined as I think a research engineer, or a kind of that time promoting the idea having a research engineer at the universities have been dramatically improved the software quality of our GPy library at that time. And then there's a more contributor to GPy. Here's a link to the contributor page of the GPy GitHub page. There's a way more people contributed. I don't want to take all the credit. List the people here are the who actually started the idea of GPy. And the GPy is also and have a relatively long history. I think this is a timeline of GPy's on GitHub. It started, you can see, like somewhere before the end of before the beginning of 2013. So I joined the lab around the end of 2013, and afterward we still have quite a significant development. You can see the activities there. And unfortunately, the development actually slowly reducing, and at the moment is mostly in maintenance mode. It is still very much usable, but there are just less new features added into it. At the end, I will discuss a bit why and what does it compare to other more recent libraries. Yeah, I will go through a few of the GPy notebook about GPy's to give you a little bit of idea about the UI, the design, and the features we have there. And if I get time, I will also dive a little bit into what is behind some of those tricks and the designs we did back in the days, maybe still useful for people to try to develop a new library and a new applications. So let's get started with some of the notebook of the GPIs about on the usage side. By the way, a lot of those notebooks you can find either there's a link on the GPI GitHub page, or there's a link also linked to here. It's in a slightly separate repo under the Sheffield ML organizations called a notebook. And there are a few of them. I will mainly go through 4 if I get time, and then if I get time, we'll talk about a little bit about the source code. First, this notebook, I think I will try to give a little bit an introduction to the UI and how you might interact with GPIs. In the lab sessions, you already probably interacted a bit with the library, so that I will go it relatively quick, but point out some of the UI components are do not necessarily special, but quite handy for GPIs. This part we just simply generate some data, and for starting the examples, it doesn't. These code are not dependent on GPI. It's just standard Python, NumPy code, and like you have already seen that in these simple examples, we try to probably regress a data where x-axis is denoted by x, and y the output is just constructed by artificial sine cosine function like this. And the starting point of the GPI UI is you basically can use the almost like those standard interface like in scikit-learn. You can dump in the x and the y, the input and output data, and it will return you a model, which is when you specify that you created the model a class, which is this is gpi.models.gp regression, that will give you a regression model. Regression here is just a more standard one with a homogeneous Gaussian noise model. And one very handy property of GPI is that you can always print the model. You can either just in notebook, you can just enter it. It would in the notebook it will display the content, or you can in a more terminal environment you can just print the model reference. It will give you a short description in terms of what is a model, what is the objective. Objective is actually the negative log likelihood. The number of parameters are free parameters for the models. The number of optimizable parameters, the idea is being like you actually can specify some parameter you don't want to, if you don't want to optimize. I will touch a bit later how to do that. And then there is a list of variables being exist in the models. In this very simple GP regression cases, we have 2 kernel parameters. They are RBF, so it's RBF.variance are the kernel variance, the RBF.length scale are the length scale, and the Gaussian noise variance is a Gaussian noise the likelihood, because we're using Gaussian likelihood. These are the value. These are the constraint. This just means that the value are positive values because all these values are expected to be positive. Yeah, just to say, you can also just print it. It's slightly more terminal environment friendly display. And you can always access the variables of the models by call something model dot. You can just take this name, for example, model.rbf.length scale. It will return you the length scale. You can print it, and you can also actually access the value using this as a reference of the actual value. It will point to the NumPy data structure used inside the model. And also, I think it still supported the regular expression search, so that if you do this, it will find all the model variables and with a length scale, because dot star, if people are familiar with the regular expression, basically means like one or more any characters. Anyway, one other handy component of GPy is it has integrated with some common visualizations which we often do in Gaussian process. For example, for regression, the most typical one is dot plot. It will give you input or output if it is 1D, input output regression plot, which is a lot of times very handy for understanding what is happening with the data. The typical things that will be plotted are the black cross are the data, the solid line and the mean, and the shaded area are the two standard deviation, including the variance.
Shen-Wen,
go ahead.
Sorry to interrupt. There is a question.
Yeah.
Can you see the question or the Q&A?
Oh,
so the
Q&A.
question.
Yeah. Constraints are active during the optimization, or they are applied to post-optimization. The constraints are active during optimization. The idea of have the constraint there. Maybe since we have the question, I just dive a little bit into the details. We actually internally do a transformation of the variables. If a variable is constrained to be positive, inside we actually will do a positive transformation. So it means like the free parameters are free for the real domain, and then the variable is represented by the default positive transformation is soft plus, or basically a transformation allow the variable after transformation to be the positive. So that will be the after the positive transformation are the values seen by the model, but the optimizer will see the before transformation variable. So that in short, yes, the constraints are active during optimizations, and optimizer will make, even during optimization, the model will make sure it's always stay positive. There's no other chat. Yeah, cool. Let's move on. And yeah, the two standard deviation are the shade areas shows the two standard deviation, including the noise variance. And there are some argument there if you don't want to show the noise variance, but the default it will. And the optimize the point optimize or point estimate of the model parameters can be done by called a dot optimize. If we want to see the progress of the optimizations, you can say the message is equal to 1 or 2, and it will basically showing visualizations of the during the optimization. You can see the variables change live during the optimization, which is sometimes quite handy if you see the variable stuck or going into the wrong direction. And previous the plot is before fit, so this is very much the default kernel parameters, the Gaussian posterior with the default parameters, which is all 1, and this is the fit, typical fit, a point estimate, a maximum likelihood fit of the kernel parameters. And then this GP posterior with optimized parameters. Anything more relevant? Yeah, another thing, you can always change the model parameters. When you do this, we will change the length scale to 0.1, and all the model internal calculation will automatically update it, and then you can just plot, and then it will plot or predict, will just use the new parameter and do everything correctly. And a brief touch to the constraint. And previously I already mentioned how the constraint, positive constraint get handled. But also beyond that, there's a few handy ones we do. One is fixed, because sometimes we just, for example, know the true value for some parameter we don't want it to go for, don't want the optimizer to change it, so we can just call it dot fix. And we can also, if you also no longer want to fix, you can call it dot unfix. And there's also a number of other constraints you can apply. That, for example, the length scale, the default one will be a positive constraint, but you can also constrain the two between an interval. Internally, what it does, it will again do a transformation from a real domain variables into a constraint variables. Those bounded constraints will actually using a sigmoid transformation function. So that's why these intervals actually are open-ended, not closed-ended. A few things. Yeah, we can unconstrain the whole models, and yeah, another handy thing. You can also set a prior. This still the model will still does point estimate instead of some sort of Bayesian inference, but adding a prior will give an additional, you can imagine, regularization over the parameters, so that you can post some prior for the parameters. Usually the prior has to match with any particular constraint the variable have, for example, length scale, are positive. Therefore, we need the prior to be in a positive domain. Here is basically giving it a gamma prior by specifying the mean and the variance, and then this will like indicated here with the A and B parameterization of a gamma distribution. This will pose such a gamma prior over the length scale, and during the optimization it will just have the additional prior. So it will do for the length scale a maximum a posteriori instead of a point estimate because of the exist of a prior. Any other things to show? I won't touch it there. Can you share the location, the GPy regression model compared to where the GP is compared with STD regression method? I'm not quite sure what does STD regression method mean here. Standard. In this library, we only have a Gaussian process model. So maybe we can take the question offline, because I still want to run to at least 1 or 2 notebook before we close the talk. And also, just very quickly, if we have a 2D data, we still have some built-in visualizations about the models. If the X is 2D, and then we actually will do a 2-dimensional those level set visualizations. But unfortunately, with the default visualization cannot handle more than 2D, because the more than 2D visualization is really hard. But in that case, you can ask the model to slice a particular dimension over a high dimension, slice of 1 or 2 dimension from a higher dimension and do the visualization. Sometimes, nevertheless, it's quite handy.
So so there is another question in the chat asking about the gamma prior and if it's updated during the training loop as well.
The prior itself, it is not. That is slightly confusing. I mean that the parameter of the prior is not going to be changed during the optimization. It will just influence the variable values, so that it has an additional constraint if you want to think in that way. But the gamma parameter, the parameter of the gamma prior distribution itself will not be changed. I will jump into another notebook because it does it slightly more details. Some model basics. I think I mostly covered most of the model basics you might need. And let me just very quickly scan through this notebook. You can set for the parameters that is not a scalar, you can do some NumPy indexing to say, like, for example, this will take the inducing variable for a sparse Gaussian process with the first dimension start from the third entry, and then you can assign them to a value, so that basically you can do a NumPy indexing and then like manipulate the variables inside GPy. That is quite handy. You can also plot the model gradient. You can, for those parameters, there's always there's also a gradient property associated to it. You can do like, for example, RBF kernel dot gradient. It will give you all the relevant gradient for the RBF, which is have 2 parameters, and it will plot them together. You can also do RBF dot length scale dot gradient. It will give you the gradient of the length scale. Constraint, unconstrained, we already covered. Optimization of the parameter plot. Yeah, this thing we already covered. And kernels. Kernel is an interesting part of GPy, because we do not only implemented some standard kernel like RBF, Matern. There's quite a number of choices in the kernel. Some even special ones like stochastic differential the equation kernels. But there's even more fancy part not existing in all libraries, that we also allow you to construct additional kernels by combining kernel functions, because we know that sum and product of positive definite functions are still positive definite kernel functions. So you can construct kernels by combining multiple kernels. For example, I think Nicolas already talked in the first day's lecture that you can combine, for example, a RBF kernel, a linear kernel, by sum of them or multiply them, and that things can very conveniently done in GPy, by just creating kernels and then just doing some linear algebra operation of it. For example, in these examples, we create RBF kernels, and we also create Matern's 3-2 kernels. The three arguments are: first is a dimensionality. It's a one-dimensional kernels with the initial I think the length, mean or variance or length scale. Variance to be 1, length scale to be 2. And similarly, Matern kernel following the same definition of the argument, and then we create a new kernel by multiply these two. Then that become a new kernel, and then you can just use that new kernel directly into any GPy function, GPy models. When the place is asked for kernel, you can just plug in that kernel in, everything will work, as if it is like dedicatedly implemented kernels. And another common one is summation. You can also add one kernel with another kernel, so you can add multiple them. And then you can imagine it is open up a linear algebra over kernels. You can actually construct a fairly complicated kernel combinations by some product various kernels together. And here are some handy plot. You can just plot the kernels that will shows you the kernel values by fixing one of the values. These are 1D kernels. It will fix the for example, the one side to be 1, and it will plot the other side. While changing the x, what is the kernel variables? It will give you some idea about what is the characteristic of the kernels. Yeah, that's a handy thing about the kernels. Any other things I want to cover? Yeah, I cover the kernel basics, and then very quickly the Sparse GPs, a slightly more complicated models. Then I have a question. Prior to the hyperparameters, can you explain again what the difference is between defining constraint and the prior for optimizing a parameters? Is a prior just used to draw starting point of optimization? Not only that, I mean, constraint is a constraint, so that it does not put on additional like you can see, like if you foresee a prior for MLP estimation of a parameters, the prior place like regularization or awaiting of functionalities, then constraint does not do it. Constraint only constrain the value range of the parameter. Say if it is a positive constraint, then it only constrain the parameter to be positive. So it does not encourage the value of the parameter towards certain value range. That is different from, for example, a prior. Imagine we are giving a Gaussian prior to a particular parameters, then like those regularization effect, it will nudging the parameter towards, for example, the means, and not going too far, not too far away from the variance, so that the prior and the constraint are do quite a different things. And also from the initialization point of view, if the parameters being given a prior, you can, if you use the functionality of the optimization with multiple restart, and then in that cases, the model will draw a random values from the prior distribution apart from one trials following the current initial values. Let's move on very briefly about a bit more sophisticated, but you probably already seen in one of the lab sessions, but just to go over it. That is the GPy models.gp regressions. We have the input output again. optimize, we choose to use LBFGS, which is a default. And this is the regressions. This is standard GP regression models. And for the sparse GPs, you will specify the inducing pointer. If you remember a bit of when I talk about the scalability of the GPIs, this is the variation of sparse Gaussian process, the collapse lower bound, so that we do not need to take care of the variation posterior of the inducing variables. We just only need to care about its input location, which is indicated as Z. You can manually specify initial values, or default it will just randomly subsampling from the training data as the initial location, but the value itself can be optimized. But like you see before, we can also constrain if you don't want to optimize it. In some cases, if we know the optimal location of the inducing point, then we just fix it, because that makes optimization much faster. And again, the visualization, this time we have those little arrows here is actually indicate where the inducing input is located. The x-axis is input, so that we have 6 inducing points. These are the 6 locations where the inducing input is. And again, the rest is similar to the regression plot. The black X are the data point. The solid line is a posterior mean of the GPs, and the shading area, the blue shading area, is the error bar, the 2 standard deviation. Yes, LBFGS is pretty efficient until you have a crazy number of parameters. Then that may get a little bit tricky, but in general, LBFGS works quite well until you hit the scenarios where you have to run mini batch training. Then the BFGS doesn't work anymore. But otherwise, the optimizer will default use BFGS, because actually LBFGS, which is actually the default choice and works normally very well. Can I set a kernel just for one problem domain? And yes, you totally can. You can specify one. For example, if you have a 2-dimensional problem, you can set one kernel covers one dimension and another kernel covers the other domain, dimension. And then if you add them together, then it's become like some kind of a typical additive cases. You assume different input dimensions are additively related. That's totally fine. There's all sort of things you can play with. More inducing points, it will get a bit better. This is just a typical sparse GP exercise. Okay, cool. We have still 10 minutes. Let's do this. I will first say the pros and the cons, and if you still have 5 minutes, I will show a little bit of the code structure. Or during that, feel free to ask questions. Then if we don't have time, then I can skip that part. I will just point out where it is located in the source package.
So we have until 10, so take your time, because we have plenty of time for questions. Okay,
cool. Yeah. So pros and the cons. And we very quickly scan through the UI of the GPIs, you probably have a little bit feeling it is a convenient GP library to start with, because you can use it similar to the way like we use the scikit-learn model. You can dump input, output there, run optimizations. It will just give you the model, and then you can do the prediction. You can do some simple visualization. Things are readily there if you just wanted to fit a simple GP model. And a lot of common GP model and the inference method and the likelihood are included. For example, if you want to use a heavy tail noise distribution like student T's, or if you want classifications, there are corresponding likelihood available there, and the inference method are available. For example, Laplace approximation can correctly handle it. And also we briefly see like the kernel construction is quite powerful. You can construct additional kernels by just sum and the product kernels together. That makes a dedicated new kernels. That's particularly powerful if you have a strong domain knowledge about your problem. For example, in your regression problems, this input dimension is that certain things that is contribute a certain way to your output result. For example, one dimension we know that contribute only additively to the output, and then we can just build a specific kernel and add it to the overall kernel. So there's a lot of things you can do there. And also another point I want to make is that while we're developing it, we actually pay a particular care about the numerical stabilities for a lot of the core components there. It will, like most of the numerical routines, it will never be perfect, but a lot of things are carefully tested so that most of the times you should be fine. If you don't throw too crazy value range or lose of accuracy representation of your data, it should be fine. Then comes to the comps. First, it's a library in maintenance mode, so that means like there are presumably less new features will come into the library, so it will still be usable and remain to be useful for quite a long time. But if you want a shiny new method that get published, it's probably not going to be available there. And second, and there's no auto differentiation because the whole development was even started before auto differentiation become a common thing available in machine learning domains. When we started, even Tiano doesn't exist. GPU acceleration was not quite a convenient usable thing, so that that times we don't have that tools. Therefore, we build those the implementations with the calculation and the gradient calculation separately. And that makes the benefit of, like I say, that we have a full control of numerical stability. Sometimes we tweak the implementation to make sure that they are numerical stable. But the downside is that if you want to have a new component, then you have to still implement the forward pass and the backward pass. That's sometimes much more work than just implement the forward pass, so that it'll make it slightly harder for implementing a new shining models, especially those more fancy models like deep GPs and other stuff. It'll get challenging, or at least require more knowledge and times to implement that. And the third is there's no GPU accelerations. The GPI only runs for the CPUs. It has a very limited dependency. It only basically depends on NumPy and SciPy, which is quite easily to use, quite easy to set up. But also, if you have a GPU, it doesn't take a benefit from it. For example, GPUs, you can probably run sparse GPs with at least 10,000 inducing point, but with CPUs, GPI normally will handle around 3 to 5,000 inducing point or the data point around that magnitude. It's harder to go beyond that level of cubic complexity. So that's the downside of it. Yeah. I see a new questions. Manual differentiation have some benefit over the auto differentiation. And yes, because you have the full control about and how the numerical things get treated. Some simple examples. For example, for Sparse GP and the Bayesian GP are VM version lower bound. There you actually can work out a multiple way of implementing the same piece of math. And they all have a slightly different numerical properties. If we ignore numerical stability and inaccuracies, all these different implementations are mathematically the same. But practically they are very different. For example, the way when you do the Cholesky's and how the Cholesky is combined to invert certain things, and then how especially at a gradient time calculations, what combine with what. And the different order and the different treatment bring a lot of numerical difference. And sometimes we will also add some we call it jitter, like small numerical terms to keep things stable, because you may notice that if a covariant matrix is close to singular, it can often be very bad. It is numerically sometimes fail, the routine fails, so that we will add some terms to just make sure it's computable. And all these things require manual tuning, and sometimes the level of can control how the backward routine goes is actually quite helpful. But having said that, it doesn't say like the more modern auto-differentiated path is necessarily numerically unstable. The people sometimes do other treatment for it to make it mostly usable. But just to say, like in these libraries, we take care with like a manually controlling the how the forward and the backward paths are implemented. Yeah, so we still have roughly 10 minutes. So let's go through slightly the kernel and the code structure of the GPIs. These are the common component there. Of course, for a GP library, there's a kernels, models, inference method, the likelihood, especially this is what I'm talking about. What I mean by likelihood are those noise models like Gaussian noise, student T noise, noise, these kind of things, and some core GP implementations where different models are inherent from. First, let's have a look at the kernels. This is under the path of the GPI underscore GPI/kernel/source. There's a lot of kernels here. Over the times, many things get implemented, and some typical one like stationary kernels will have a size and acceleration built in. For quite some time, it caused troubles when the people try to use it in non-Linux environment, for example, Windows, because the size and compilation require compilers. Anyway, maybe we dive into the base kernel so that give you a little bit idea what the UI and what I mean by the manual auto differentiation. And this is a class, kern is the base class of all the kernels inherent from. And their standard their standard UIs are, we will always ask for the input dimensionality of that specific kernel. Remember that specific dimensionality may not have to match with the overall dimensionality of the problem, because we can have a 1D kernels applied to a 2D problem and only responsible for one of the dimensions. So that the active dims actually take care to say, like in the original problems, what the dimensionality it take care of. If you want, you can give a name. And that was the by the in the day that we manually coded some GPU acceleration into the models, but that is not fairly useful now because of the rapid change of the GPU environment. The common APIs, if you want directly use a kernel, they are handy. One is .k is basically calculating the covariant matrix. It takes two arguments, x and x2. If you omit x2, it will just calculate the covariant matrix x with x. And if you specify x and x2, it will calculate the covariant matrix, cross covariant matrix between x and x2. And this class is expected to inherited by all the kernel concrete kernel implementations. We have a dedicated function to implement the diagonal because it is way more efficient, and sometimes even the scalability issues if we first compute a full covariant matrix and take the diagonal, because imagine if we have the n data point, and then this k diagonal directly will only take a linear complexity, but computing the full matrix and take the diagonal will be squared. So that's why we have a dedicated function to compute the diagonal entries of a covariant matrix. Size statistic you can omit for the moment. And then there's a gradient part. This is a typical things I talk about when we not doing auto differentiations. And this is the functions expect to calculate the gradient of a kernels with respect to the input x. And the way it happened, if you know a little bit how the auto differentiation happening, it's actually the similar ways happening underneath. So that the way the gradient happens is where this function will take the gradient of the final objective with respect to the output of the covariant matrix. So that this will be the DL, DK. L is a final objective of the model, and the K is the output, which is a kernel we try to differentiate with or through. And so this basically takes the upstream gradient gradient component. And what this function does is that it will take the gradient from the upstream calculation and returns the gradient with respect to x based on the upstream gradient calculations. If you know a bit like the gradient calculation chain rule, so what it does, it will basically do dl dk transpose and multiply with the dk dx. That is what is happening, and specifically it will be implemented in these functions. And some tiny details are these are in the this is the matrix forms, and the returns will be in the shape of x. There's some other component of the gradient calculation. For example, do the gradient for the x2 component, and the return for both of them. And there's also for the diagonals. I won't go into detail, but the idea is similar. And also there's also function called to update the gradient of the kernel parameters given some upstream gradient. Yeah, this is in general how the gradient calculation of the kernel looks like. There are some specific implementations, sometimes only used for some model, because depend on the way it is being used, there are sometimes slightly different interface. But if you ever implemented a few of these gradient x, and even if you only want to do standard GP regression, you just need to implement this too. It should work. That's the kernel. I think how many I can run during these few minutes. These are the folders with all the models. It's located on the gpi /models. You can see there are quite a lot of them. So far in the summer school and the presumably lab sessions, we mostly, I think, covered the GP regression and the sparse GPs. If you want to see, it is located as this is GP regression class. And if you want, we can just very quickly look into it. It inherent from the core GP implementation class. And it just specify a few things. Basically, it specify the likelihood is a Gaussian likelihood, and then is mostly an empty body, because all the standard GP calculation is already done in the upstream class. One presumably interesting model. This is the sparse GP regression. This one. And one presumably interesting model would be the GPLVM models. I don't think we covered in this summer school. This is a type of GP model used for dimension reduction. Instead of taking X and Y, it only takes Y because it's a dimension reduction. It takes how many dimensions of a latent space you want to estimate, and how to initialize them by default PCA. And or you want to manually initialize them if you specified X, what kernel you expect to use, and then just hit optimize. It will just does it. That's a models for the sake of time. Let's quickly look at the likelihood. We have a few standard ones. Gaussian is most standard. And we also implement a few, for example, Bernoulli for binary classifications. We have Poissons for integers. We have student T. I think we have a classification one. Yeah, no, not a multiple output. Maybe the extension of Bernoulli's. I wasn't exactly sure now. There are examples in that folder about the GP classifications. And anyway, these are the likelihood. And it basically implemented how from the F to the Y is being handled. And most of these likelihood functions are work with Laplace approximation, so that Laplace approximation will try to infer the posterior using Laplace approximations to infer the GP posteriors. And yeah, and I won't go into details about how it's being used. And also a few other things here. This is optimizer. We are only using this. Some of them are not live in this repo. These are the inference classes we're using here. Some interesting component. Well, DTC maybe. This is the inference functions we implemented to handle sparse GP and related sparse GP family of inference functions. There's a particular reason called var DTC, variational DTC, because of the similarity of the variational sparse Gaussian process lower bound and the DTC approximation in the history. And the core function is here, inference. It takes the kernels, input, inducing point, the likelihood. Usually you only expect it to be Gaussian, and the y, and some y metadata. I think it will take care of the some noise Gaussian variances. And if there's a mean function, it can take a mean functions and some helper variables for the model to handle. And you can see these are the implementations. Back in the days, it takes quite a lot of code and effort to implement such an inference function, because we're not only doing the forward pass. Usually the forward path is finished until we do the forward and the backward component all together. And you can see all the DLD something is for the gradient calculations. They are typically take a way more line of code than the forward calculation. It is also quite intuitive, because for the forward one, you have only calculate for one value, but the backward you have to calculate for every variables involved in the calculation. It's already 59. I will stop here. And if people still have some remaining questions, can ask. Otherwise, thank you all for your attention.
Thank you very much for the talk, Sen-Wen. I think we have a couple of minutes for questions. So do people have any questions? And I mean, I know you have been asking already during the talk, but is there anything else you would like to ask Sen-Wen?
I think there's one question I didn't ask in the Q&A.
Yeah, one about the kernel, right?
And there's a follow-up one, and is there automatic way to find the kernels implemented in GPy? That's a bit of a tricky question. And we have a documentations which is auto-generated. Typically, all the kernels are available. No, sorry, I have to go to the real GPy repo, which is here, and I just want to point you to the dog. It's a shame I haven't clicked the things for a long time, and I'm a bit struggling finding the dog. It's not a tutorial. Online tutorial. Yeah, this is the GitHub thing. Yeah, online documentation. Yeah, this one. Here's it is auto-generated, and it will list all the kernels if you want. And it's basically the doc string generated from the kernel path, so that you can either look at it somewhere here or look at it in the source code is the same. And these are basically all the kernels available inside GPys. And yeah, I would suggest to read or even read the source code a little bit before applied, because I think I remember I get a question about for example, periodic kernels. I think there's more than one implementation about the periodic kernel in GPys. There's one version only implemented for one dimensional, because following the GP textbook, but there's some there's another periodic kernel class is actually can generalize to multidimensional periodicity. Yeah, just to say that. Let me stop here.
Thanks, everyone. Well, I think we can stop here. We have a 13-minute break now, and we can reconvene at 10:30 with the talk of Aki Vetari. So thanks, everyone, again.